Hey, well, we are ready to get started with our water resources engineering review session. We took a week off last week for spring break. Hopefully you guys were able to sign up for the exam and get going here, but we're going to continue on. We've got a few weeks left of live review sessions here, and tonight we're going to jump in with water resources engineering again. So if you haven't downloaded the questions, they're in a link below, or they should be, and I did just tweak one of the questions right before we started and re-uploaded that, so you'll see it once we get there, but it shouldn't be anything too much. So with this session, we're going to be talking about water resources engineering. This is 10 to 15 questions, and this is the NCEES spec right from NCEES. So this is what they say is going to be on the test. I sort of broke it up into H&H and environmental here, and I mean, some of these pieces, like for example, collection systems. You could put collection system stormwater with H&H, but wastewater with environmental. So there's some overlap here, but we're going to jump in and kind of hit some of the major equations. We're not going to hit all of them. I wish I had time to do all of them, but I think we're going to be pushing it just to get through some of these tonight. If we need to, we'll break it into a second session, but hopefully this is good for you and it works. So without any further, we're just going to jump in and get started with question number one. So question number one, if we get some, there we go. So question number one is a hydrology question. So hydrology has to do with water falling, right, and running off a site. So obviously the big concern here with hydrology is before development, you got a bunch of trees, grass, and you have a lot more room for that site to retain water. And after development, right, you have a lot more pavement, maybe developed space, and there's going to be more runoff. So one of the ways of getting runoff is by using Q equals CIA, so the rational method. And here we have a project site determined to have rainfall intensity for its design storm as shown in the curve below. So this is a rainfall intensity duration curve, right? So generally you might get that really quick blast and you get a bunch of rain right away, but it doesn't last as long versus a long, slow drizzle, right? So we have our intensity duration curve. And the total site has 10 acres. So we have two areas, two catchments here, area one, and that should say area two. So if you guys were in, well, I'll repost this with area two. So that's one other correction that I have to make. So, so we have area one, area two. One area is 4 acres, one area is 6 acres. And, area one, everything in area one is going to drain to this catch basin. Okay. And then everything in area two is going to drain to this catch basin. And in between, the flow goes from catch basin 1 to catch basin 2. So that's kind of the way this site is set up. And and what we see here is the composite rainfall coefficient for the entire area is about 0.4. Velocity of 2 feet per second is assumed in the storm sewers. And based on the parameters given, the discharge from this site is most nearly. So this is where, again, when we take a look at our reference handbook here, we're going to be in the civil engineering section, I believe, and what we're going to be doing here is we're going to be taking a look we're going to go past the structures, past geotech, and I like sort of scrolling through this a little bit, so you can kind of, and maybe you should do this too as you're studying for the FE, but the nice thing about scrolling through these, sometimes you get kind of used to where things are, okay, and eventually you get past steel, right, and past steel, we get there, we're getting there, we get to hydrology, water resources. Right, so we have the NRCS method, and we have the rational formula here. And anytime you're given a runoff coefficient, typically you're going to be using this Q equals CIA. So, that sounds easy enough. All we need is the runoff coefficient, intensity, the watershed, and the peak discharge, right? So that's the formula we're going to use here. So we know that we're going to say, right, Q equals CIA. But then what we have to do is we have to figure out, well, okay, we know the area is already 10 acres. So we know the area, and we know C, right? So we know the area, we're actually given these two parameters, right? We're given the area of A, we're given C of 0.4. Really the only thing that we have to do here is find the intensity. And some of you are probably gonna be tempted to come here and just, pick a number. And I'm just reading this for a second too. Did I? Oh no, I think we're good. Oh, sorry. So as we go through here, what we're going to do is we have to find that intensity. And to find the intensity, what we're going to do is we have to first solve for the time of concentration. So what's the time of concentration? The time of concentration is essentially the time until you have all of the water kind of concentrated at your outflow, right? So with what we have here is, it's like I have a house that's next to a stream, and it might start raining, and then about 20 minutes later, that stream is really rushing. Well, what happened? It took 20 minutes for that stream to get really full with all the runoff from all the different areas hitting that stream. So kind of the same thing's going to happen here, right? What we have is we have two different areas. Right, we have area 1, and we're bringing water in from area 1. It comes down to this catch basin, and then it goes through the storm sewer and goes out. So what we want to do is we want to find the time of concentration for that area. So we're going to start with, like, I'm just going to call this TC1, and that's going to be our time of concentration for that area. So all that we have to do here is, well, we say, well, we know that it takes 6 minutes to go from the most remote point to the catch basin. So we're going to start with 6 minutes. And then we're going to add the amount of time it takes in the storm sewer. So in the storm sewer, we know the sewer is 600 feet, right? So 600 feet. And we're told in the problem that we have 2 feet per second. So velocity 2 feet per second. So how long is it in that sewer? Well, to get the time, we're going to divide by 2 feet per second. But you'll see here that the units aren't the same. So we have minutes and seconds. We need to do some conversions here. Our duration for our curve here is in minutes, so we are going to go with minutes. So what we want to do is we want to multiply by, on the bottom here, I'm just going to extend this a little bit, but we're going to multiply by 60 seconds per minute. And this time of concentration, if we do that out, what do we do? 600 divided by 2 divided by 60 is going to be 5 minutes. So this is total time of concentration of 11 minutes. So when the rain starts falling, it takes 11 minutes to go from the most hydrologically distant point on that watershed to the catch basin, through the catch basin, and out of the sewer. Okay, out of discharge off the site. So then let's look at time of concentration 2. And what we see here is this one's actually a little bit easier, because what we're doing with this one is we're saying, okay, we're starting at the hydrologically most distant point, and we're going to go to catch basin 2. And then we're going to go off the site. Okay, so with this, we actually don't head through the storm sewer at all. And for this one, we're just told that time of concentration 2 is 10 minutes. So all that we're going to do here is we're just going to say, well, this one's 10 minutes. And now comes the question, well, what's the time of concentration? Is it 10, is it 11, or is it 21? Well, again, let's think. When rain starts falling, it starts falling at the same, this whole 10-acre site all at the same time, roughly within, a couple seconds probably. So what we're doing is we're trying to say the time of concentration is the time from the most distant part to all hit the discharge point at the same time. So we're going to take the longest time of concentration here, and we're going to say that the 11 minutes controls, right? So this is going to be the worst case for your intensity, essentially. Once you hit that 11 minutes, all the water's flowing from all over the site, and that's going to be your worst case. So that's the storm, intensity is going to be the max. Essentially, is going to be the storm intensity is going to be the max at 11 minutes. So if we have that, we can come back up here now, and we can use our rainfall intensity duration curve, and we can take a look at this, right? So I'm just going to get a line here, and if I take a look at a line, essentially, let's take this here. So I'm going to come in at 11 minutes, which is right around here. I don't know if you can see that. Yeah, you can see it well enough, right? And then what I'm going to do is until I hit this curve, and then I'm going to come over. So what we see is this curve is, we hit this curve somewhere around that point, okay, which is roughly 5 inches per hour. So what we've just done is we've gone and we've gotten our I. So this is our I value of 5 inches per hour. So when we come back and solve our formula now, essentially all that we have to do is we have to say, well, Q equals C, which is going to be that 0.4 that was given, times what? 5 inches per hour times 10 acres. And some of you are looking at this and saying like, man, those units are really nasty. And to be honest, they are nasty. But that's okay, because when we look at the rational formula in the handbook, right? So in the handbook, what are we given? We're given a watershed area in acres. We're given the runoff coefficient, which is unitless. Well, it isn't really unitless, but it takes all those conversions into account. We have rainfall in inches per hour, and we have peak discharge in CFS. So the beautiful thing about this equation is our units actually work out for themselves, and we don't actually have to do any conversions, right? So we get, what do we get? We get 0.4 times 5 inches per hour times 10 acres. And with that, we just get 20 CFS, so 20 cubic feet per second. So that's kind of the first step here, is just to take a look at flow from a site. And, you know, you might be given a duration intensity curve, you might be given some catchments, you might have to solve for the time of concentration. But again, what we're looking for is the maximum time of concentration for the peak intensity for this storm, you know, and that's going to give us the runoff for that design storm. Okay, so we can come back up here. We got our 20 cubic feet per second. So we're pretty good. All right, so that's pretty cool. And hopefully that works for you. If you do have questions, feel free to drop any comments. So the live, I am trying to monitor the live chat as well. So, or if you're watching this video later, you can put comments down below and I will do my best to respond to those as well. So with that said, there is a slight delay between, I think, for buffering for what goes live and what's on the chat. So if I don't see it right away, let me know and I will try to get to it. All right, so as we keep going, let's go to question 2. So question 2 is another hydrology question, and this uses an alternate method, right? So this uses a method this uses the SCS method, right? So, or NRCS. And as we look at the handbook again, there's 2 methods kind of for predicting runoff. And the rational formula gets a lot of use. The SCS rainfall runoff method does as well. So they're both good to know, but they produce different things. They both produce Q. So they both have these equations for Q. But it's interesting to note here that the rational formula gives a peak discharge in CFS. But what does the NRCS method do? It gives a peak discharge Q in inches. So the NRCS method, it's based on NTR 55, and maybe you've seen that before, but there's like a bunch of forms. These forms get played out in programs like water type resources programs with that, like a HydroCAD, for example. So you can plug these in and use them there, but it's good to kind of understand both methods a little bit as well. So we're going to go over this one, and this is the way this works is the land system is essentially broken up into curve numbers. And what the curve number is it's a reflection of how much runoff will come off of that site. So an impervious area like pavement will have a lot of runoff. It's not a curve number of 100, because even though, you know, the pavement will pretty much take all of that water and shed it off, okay, it's not going to shed off 100% of it. It's going to shed off most of it, okay? And that's okay, right? So that's okay. We can take a look at that and still be okay with it. Okay, so just give me 2 seconds here to fix one thing on my stream, and I think that'll be a little bit better. Okay, so what we're going to do is we're going to find a curve number, a composite curve number for this site. Okay, but basically what we're given here is residential development. We have pavement, lawn, open area, CN values given. So we have a 100-year storm that produces, let's say, 7 inches of rainfall. Okay, maybe you live in a part of the country where you get more than 7 inches. The part of the country I live in, we get about 7 inches for a 100-year storm. The discharge from the site, assuming no other inflow, is most nearly. So what is the discharge? Well, what we're going to do here is we're going to use these equations, right? We're going to use these equations. We're looking for a discharge. We're looking for inches. So when we come back to this, we're going to look for inches, which is another big clue that we're going to use the NRCS method. But anytime you see a curve number, that's where you're going to go. So runoff in inches we have to go through this, but really all of this depends on the curve number. And what you see when we come back to the problem is we have multiple curve numbers. So in order to get the curve number, what we're going to need to do is we're going to first need to find a composite curve number. So what we're going to do is we're basically going to say, we're going to take the site and we're going to say, okay, we've got curve numbers for each of the individual catchments or areas or, you know, parcels of this type of thing. What's the curve area or the curve number going to be for the composite site? So the way that this works is it's essentially like a weighted average, okay? And to find it, we're essentially gonna, let me write down a formula here. This is not in the handbook, but it's just a weighted average. So the composite curve number is gonna equal essentially the sum of the areas times the curve number. So the individual areas times the individual curve numbers divided by the sum of the areas. Okay, so what we have here is we have our areas, right? These are our areas, and we have our individual curve numbers, and that's it, right? So that's all. That's once we have that, this is pretty good. But what we need to do is we need to come up with essentially a third column where we're going to take A times Cn, right? So if we do that out, we're going to just get some numbers here. We're going to get 2.5 times 74. I got 185. Okay, 8.5 times 80. Well, 8 times 80 is 640. 8 times 90. So I think this gets to 680 here. 1.5 times 98. Again, that's that impervious area, and that's going to be 147. So now if we sum these, right? If we sum this column and we sum this column, we're going to get some values here. So if we sum all the areas, 2.5 and 8.5, that's what, 11, and then another 1.5 I think is 12.5. And if we add up 185, 680, 185 plus 680 plus 147, we're going to get 1012. All right, so this is how we get a composite curve number, and essentially what we're going to do is once we have that weighted average, we'll be able to go ahead and solve this problem as well. But once you have the 1012, we're going to divide that by 12.5, and we're going to get a weighted curve number of about 81. Okay, so 1012 divided by 12.5, it's like 80.96, and we're just going to round that to 81, which is good because that gives us what we need for these next pieces, right? So if we come back to the handbook, what we see here is we have two other formulas that we need to take a look at. The first here is the S value, and the second is the Q value. So let's write those down and solve them, okay? So I'm gonna come back here, I'm gonna do a second step here kinda, and I'm just gonna say NRCS SCS equations. So we have two equations. The first one was S equals 1000 over Cn, okay, minus 10. And what we're going to get here is 1000 divided by 81 minus 10. And I get a value, if I do that, 1000 divided by 80 point, I'm going to even go to 80.96, why not? And then subtract off 10, and I got like 2.35 roughly, right? So 2.35. And then the second formula was the Q formula, and the Q formula is a little bit more, you know, it has a little bit more going on, but we're going to say Q equals P minus 0.2 S in parentheses squared divided by P plus 0.8 S. Okay, so just two formulas. This gets the plug and chug, but probably if you see a question like this, there's going to be maybe some combined, you know, or composite curve number that you have to figure out. Maybe they'll just give you a curve number straight up, but at least this question kind of shows you all the different pieces that I think they could reasonably ask you on the FE, because they're not going to get into the other parts of it that in TR 55 they start using charts and tables and those sorts of things that are not included in the handbook. But this is a legitimate question that I think could show up. So what do we have? Our total rainfall here was 7 inches. So if we plug in, we get 7, you know, inches minus 0.2 times our 2.35. all over, all that has to be squared, and we take that all over 7 plus 0.8 times our 2.35, and that's going to give us another value. So this is good calculator practice, if nothing else. I'd suggest you work through these or pause this and take a look at if you can put this into your calculator quickly and efficiently, because that's going to be something as well that you're going to have to do on the exam and get it right. So when I put that in, I get like 4.8. So 4.8 inches. And again, our units work out where we have inches, and we end up with 4.8 inches of runoff from this site. So even though we have 7 inches total of rainfall, right? So we have 7 inches total of rainfall. 2 inches is either getting infiltrated or retained or somewhere. It's not going off the site. Okay, it's getting soaked up and staying on the site. All right, so question number 2 is done. All right, so if you have questions on it, definitely drop a comment, but hopefully you've seen some of this stuff before, and hopefully it makes a little bit of sense as we're going through this. So I'm just going to move this up just a little bit to make a little bit more room here. All right, next question is a conceptual question. This kind of gets to what we were starting with in the first place. Has to do with the idea of runoff, right? And in stormwater management, the initial abstraction. So this is kind of the key word that we're looking for here. The initial abstraction accounts for all of the following except. And maybe you never took a hydrology class in your undergraduate career or set of courses or program of study that you had to do, but this is one of those concepts in basic hydrology that is going to make a difference. So just like you're going to have basic kind of curve numbers that have an impact of, or have a that account for that initial infiltration. The initial abstraction kind of does the same thing. So the initial abstraction has to do with the idea that when water hits the site, there's an initial amount that gets soaked up that doesn't actually go off the site. Right, so that's going to be your initial abstraction, and with that in mind, now we're looking for, okay, well, that initial abstraction, you have a dry site, you get it wet, there's some of that water is just going to get the surface wet, it's not going to go anywhere. Okay, and that's the initial abstraction. So infiltration, that accounts for that initial abstraction. Evaporation, right? You have a really hot surface, you hit it, you're going to get some evaporation right away. Okay, retention. Retention, again, that's going to be, you got little pockets and divots, even in asphalt, right? Even in asphalt, or you have some little pockets, divots that are going to hold on to water. So these all hold water, right? These all hold or retain water. That all accounts for part of your initial abstraction. And obviously you could have a retention basin where you're retaining a whole bunch of water, right? But that's not the initial abstraction. The initial abstraction is just you have the surface roughness. Even in like pavement, for example, you got surface roughness, little divots, little holes, little pock marks that are going to hold little drops of water. So you don't get 100% of that water running off. And obviously in soil, you're going to probably have a little bit more, okay? And what's left here is runoff. So the initial abstraction is not runoff. Runoff is kind of the opposite of the initial abstraction. All right. So concept question. I could see concept questions like this. I mean, have you taken a hydrology class? Do you kind of have an idea of what that looks like and how it's going to play out? So I don't know. We got a handful of conceptual questions on this. And some of it comes from when I was working consulting full time, and I worked for a water resources dam engineering firm. So we did a lot of different things from stormwater through dam design and all that sort of thing. So some of that's going to come out in some of these concept questions that I throw out here to you. But hopefully they help broaden your knowledge. And that's kind of one of the things that I'm trying to do with these review sessions, is hit all the topics, but hit them in a way that broadens your knowledge and perspective. So let's keep going. So question 4, concrete line channel is used to convey water flow between point A at a surface elevation of 510 and point B surface elevation of 508 meters above sea level over a distance of 2 kilometers. The surface roughness coefficient of the concrete is 0.012, and this 0.012 is one of those values that should set off kind of triggers in your mind as to what you need to do here, because what the question then it goes on to ask is the flow conveyed by this channel in cubic meters per second is most nearly. So we got to get flow, but that surface roughness coefficient screams, and hopefully you're remembering, it screams a certain formula. But if you don't know what formula it is, you can come in here and start to look and say, uh-oh, I don't know, where is it? There's Darcy's law. No, not Darcy's, not Dupuy. You know, we got some things going on here. Where is it? It looks like right there, Manning's equation. Okay, we have an n value here, a roughness coefficient that we're going to be using. So this gives us a formula, and I'm actually just going to copy this formula over. Why not? So if I copy that formula over, let me just do that quickly, and we will maybe make this work a little bit better here. But let's take a look at this formula, and I'll come back, and hopefully this will make it kind of nice for us so that we can put it all together and see what the handbook says all at the same time. Okay, so here's our Manning's equation, and this is what we need to solve for. So that's a little small, but hopefully it's readable. So we need to solve this, right? And we have a few different things. We're given n, that's good. We know that's 0.012. We know this k value we're using imperial or SI units. I'm sorry, we're using SI units, so this is going to be 1.0 for SI units. What else do we need? We need A, so we need the area of this thing. We need RH, which is going to be the hydraulic radius of it, and then we need the slope. So let's just work through each of those pieces, right? So let's just start with each of those pieces. So we know that K equals 1.0. We know N equals 0.012. What's next? We're looking for flow, so we're going to need the area. The area is going to be the area of flow. So I'm going to just highlight this here. So if I highlight this area, right, this is going to be the area of flow that we have to deal with, right? So that is our area. So what is that? That's just going to be, well, this is a trapezoid. It's so we're going to do 1/2 of the bottom height, which is 5 meters, plus the top height. So 5 plus 8 is going to be 13 meters. So that's our average height, or I'm sorry, our average width of this thing. And then our height we know is this 3 meters. So if we multiply by 3 meters, what are we going to get? We're going to get 1/2 of, what's this, 18. So that's 9 times 3. It's going to be 27 square meters. And what's RH? So the next parameter that we have here is RH, or the hydraulic radius, which is just A over P. So they tell us this is A over P, and this is where P is the wetted perimeter, right? So P is the wetted perimeter. And what that looks like here is, I will highlight this too, but the wetted perimeter is the parts that are wet, right? So the parts that are wet. So we can just add these distances up, and if we know we have 3 and 4, we're going to get a 3, 4, 5 triangle. And I mean, you could use Pythagorean's theorem there, but each side is going to be 5 meters because it's consistent. I don't know. I mean, I don't think that if he's going to try to trick you a ton with like crazy dimensions or anything, it's more so, do you know the concepts, right? So what do we have going on here? The perimeter is going to be, well, what, 5 plus 5 plus 5 is going to be 15. I'm sorry, that's the perimeter. So let me start over. The hydraulic radius is the area over the perimeter. So we have 27 cubic meters. I'm sorry, square meters. Man, it's early. And divided by the perimeter, which we said was 15 meters, right? So that's the that's the area. This is the area, right? Divided by this perimeter, and that's going to give us what? 27 divided by 15. I think that works out to be 1.8 meters. Okay, so what's our next coefficient here is S for the slope. So this is feet per feet or meters per meter. So again, just looking at those units, understanding those units is huge on this test. Just knowing what the equation or what the units are in each equation is going to be super important. So we get a slope here equal to Well, we essentially have the fall, which is going to be, we go from 510 down to 508. So that's, 510 meters minus 508 meters. And this is over a distance of 2 kilometers. So 2 kilometers times what? 1,000 meters per kilometer. So what do we essentially get 2 divided by 2,000. And if you're not super confident with your decimal division here, that's okay. You can put this into your calculator, and there's no shame here. I get 0.001 meters per meter. Okay. Once we get that, right, these are all our variables. Once we have all our variables, we can just start to plug and chug here into the equation. I've also seen some problems, where it's like it might not be a full Manning's question. It's just find the hydraulic radius, and again, with that, you're just looking at the area divided by the perimeter, and that's what it's looking like. So what do we get here? We get Q equals 1 divided by 0.012 times what was next? So times A. So the A here was 27 meters squared, and times the hydraulic radius of 1.8 meters to the 2/3 power. So make sure you know how to do that one on your calculator. It's not just a square button. You have to put the 2/3 in there. Make sure you get it in parentheses unless your calculator is in the mode that doesn't need parentheses. But the good thing here is all the units work. So we have meters squared, meters, and the slope in meters per meter. So all our units are consistent, and when we solve this, hopefully we get the right answer. That's always good when you get the right answer. But 1 divided by 0.012 times 27 times 1.8. And then what I do here is just to the 2/3 power. You can put 2/3 directly in to the calculator, but make sure you hit that over button to get down again from the calculator, times 0.001 to the 0.5. So I get about 105.3, or most nearly 105 cubic meters per second. Okay, so just using Manning's equation, but this brings up a couple different topics. One is just the hydraulic radius, 2 is the slope of a channel, and 3 is kind of this idea of how to calculate the flow. All right, so question 4 is done. All right, got down back to question 5 here. So we've got an 8-foot wide rectangular channel, carries 200 cubic feet per second of water at a depth of 1.5 feet before entering a hydraulic jump. So what's a hydraulic jump? I guarantee every one of you has probably seen a hydraulic jump today. Do you know where? If not, you'll never wash your hands again the same. Because when you're washing your hands, let the water go for a second. Just look down and see what happens. Right? What happens is that water hits the sink bottom, right? And it splays out, and then all of a sudden, at some radius from the center, it jumps up, right? So it goes from this fast, smooth flow to a jump kind of, smooth flows, but that's a hydraulic jump. And you'll see that anytime you wash your hands, hopefully. But where does that occur? A lot of times it occurs like, for example, if you have a spillway, right? So we've got this spillway, and let's see what happens with the spillway. Well, what's going to happen with this spillway is we're going to come down with water that's fast and furious kind of off this spillway. It's going to go down, and then the slope's going to kind of flatten out a little bit. It's not going to be as steep, and it's going to, jump up here, and the velocity is going to slow way down. Okay, the velocity is going to slow way down. So there's going to be this jump here, and what we're trying to do is we're trying to find essentially this height. Right, so we're trying to find this height here. This is going to be, I'm going to call this like height 2, okay? Or actually, to be consistent with the notation in the reference handbook, I'm going to call that y2. Well, where's y1? y1 is just this value here, which is going to be the supercritical value, right? So there's supercritical flow, and there's subcritical flow. And those are two kind of concepts that you need to understand a little bit. But we got this really fast water. It's gonna go supercritical, and then at some point, if the slope lessens, and especially downstream of a dam, you see that, or downstream of a spillway, you'll see that where it goes to where there's all of a sudden this jump and it goes to subcritical. So what we want to do is we want to find that. And this brings up a couple of ideas that I think are worth talking about in kind of this hydraulics section. But what we're told is we're told that we have an 8-foot wide channel, 200 feet per second, a depth of 1.5 feet. So up here we have 1.5 feet. We've got a Q here of, Q of 200 CFS, cubic feet per second. So what we want to do is we want to find our hydraulic, we want to find an equation for this hydraulic jump, and we want to go and calculate what that looks like as well. So we're going to come back, and what we see here is we're on the same page. So we've got a hydraulic jump formula here. Why don't I snip that too and bring it in just to make our lives a little bit easier, so we have less jumping back and forth. So we have a little bit less jumping back and forth here. So if I bring this over and come back, we're going to use this formula now and bring it in here. Okay, so this gives us a hydraulic jump, and it's a little bit more complicated than what we just did with Manning's, because the hydraulic jump, it gives us this Y2 value, which is great. We found our equation, we know what to do, except it brings us to this idea of the Froude number, right? The Froude number is it's a number that you can calculate to basically figure out whether or not something is supercritical or subcritical. And I mean, that's a kind of a simplified version of how to say it, but here in that reference handbook, we're given a Froude number, but we have to come back to find out how to calculate that Froude number. And here it is. So for rectangular channels, we have a critical depth. We can calculate the critical depth, but we can also calculate the Froude number. And what we see here is if the Froude number is bigger than 1, we're going to have supercritical flow. And if it's less than 1, we're going to have subcritical flow. So what we would expect is, on one side here, the Froude number is greater than 1, and on the other side, the Froude number is less than 1, right? So we go from, we transition here, and we have to go find it. So what I want to do is I want to calculate the Froude number so I can go and calculate my depth, because that's what the problem is asking. Okay, so I'm gonna take my Froude number back here as well, and let's pull that one in as well. So if I snip that one in, and on the test, you're gonna have both. You're gonna have 2 screens here. I don't have that luxury as much with what I'm doing, and hopefully this works for you as well. So I'm gonna bring this down here because I want to get this equation right, and I don't want to screw it up. Okay, so I'm going to bring my Froude number equation in, and let's solve for the Froude number, and then we can solve for our depth downstream of the jump. So step 1, we're just going to solve for Froude, and that's going to look like this. So we're going to have, what do we have? We have the square root of Q squared. So Q here was 200 cubic feet per second, times T, and I do have to come back to the handbook for a second here, because T is, where did it go? Where's T? Here's the hydraulic depth, A over T, and we actually, I think if we come back one page, where the T is the width of the water surface. So T is going to be the width of the water surface, and we're told that that width is 8 feet here, so we're going to use times 8 feet, divided by, what do we have? We have G. So G for English units is 32.2 feet per second squared. Okay, so if you don't know that number, you probably need to memorize it. It's like 9.81 meters per second squared for metric. Okay, and then what's next? We have times the area cubed. So upstream, the area is going to be 8 feet times 1.5 feet. And we have to cube that. So we do all this, what we're expecting is that Froude number is going to be bigger than 1, meaning it's supercritical, and hopefully the problem was written correctly. Sometimes when you're writing your own problems, you don't necessarily make everything right, but I think I got this one right. So 200 times 8 divided by 32.2 divided by, what do we have, 8 times 1.5 in parentheses to the 3 and I think I screwed something up. So what did I screw up? Oh, I forgot to square my flow. There it is. So it's good to put things in your calculator and not just trust your notes. But yeah, so if we put that square in, and let me go back. How did I know something was wrong? Because when I calculated it, I got like a fruit of 0.16. I'm like, wait a minute, 0.16 is less than 1. I don't like that. What did I screw up? And that helped me to understand where my mistake was in this, right? So I knew I did something wrong and I forgot that square. So you know, you have to look at the formula, but you have to write the formula correctly. And I got a value of about 2.4, which again is greater than 1, which means you know, it's the fruit is greater than 1, and that's super critical. So that checks, right? Once we have that, all that we need to do now is find our Y2 depth. And that's just, again, that becomes kind of plug and chug here because we have the equation Y2 equals Y1. So Y1 was 1.5 feet divided by 2 times minus 1 plus the square root of 1 plus 8 times the fruit number, so 2.4 squared. And if I wrote down all my squares correctly, I think Y2 is going to equal, well, let me just double check. So 1.5 divided by 2 times minus 1 plus the square root of 1 plus 8 times this 2.4398, depending on how much you want to get in there. That needs to be squared. Yeah, so I get about 4.4 feet. So hopefully you were able to get that as well. But the reason I wanted to bring this question up is it kind of, are you going to get this exact question? I don't know, maybe not. But the idea of supercritical, subcritical flow is one of those ones that I think could show up for sure. So just the idea of, you know, velocities and flows and that sort of thing. And I think it's something that could show up, because whether you see the fruit number here or maybe in a different place, I think it could potentially show up. All right, you guys are quiet today. No major comments, but if you have any comments, let me know how we're doing. And you know, we'll keep going. So if I make mistakes, let me know, or just put your answers in the chat box and we'll see if you guys get the same thing as me. All right, so here we go. So we have a pump, right? And this is a pump equation. So last time when we did fluid mechanics, we were looking at the Bernoulli, and now we're going to take a look at the energy equation. So the energy equation has to do with energy losses. But let's take a look at this question and see what it says. We have a pump is used to lift water from a reservoir with a surface elevation of 210 feet. So let's draw our reservoir down here. So we've got a reservoir. You know, we got a reservoir here, and maybe we have some, you know, water level. Okay, so this is open to atmosphere, and this is our reservoir full of water. Okay, and what we're going to do is, I mean, this is one of those things where maybe you're doing an agricultural thing and you need to lift water to something. Maybe it's a fire application, but you're going to put some pump, you know, sitting here, and you're going to put a hose in, a hose out, and you're going to go up to a discharge point up here, which is at an elevation. Let's take a look at what our elevations are. So we start at an elevation of, actually, I think the way that I said is the pump elevation is 210. So we're gonna maybe let's maybe move this pump down just a hair. Oops. Let's move the pump down just a hair here. So we'll move the pump down so that it's at the same elevation as the water surface, and we're not gonna introduce like anything too crazy here. Okay, so we're gonna basically stay there, and then we're gonna come up to a discharge point somewhere, you know, up at this point. Okay, what elevations do we have? Well, we start a reservoir surface elevation at 210 feet. So we've got, you know, 210 feet here, and we have a discharge at 235 feet. Okay, we want a pressure at this point, a pressure at point 2 of 50 psi. So whatever application they're doing, we need a pressure of 50 psi. The pump flow, right? So you got some flow in this thing. That's 100 gallons per minute. Okay, and what we're going to do here is we have a 2.5 inch diameter hose with a C value of 135. And when you see that C value, that's hopefully gonna tell you that we need to look at friction in this pipe, okay, or this hose. We need to look at friction, and hopefully you know that we're gonna look at using the Hayes and Williams friction factor. Now there's a couple different ways of looking at friction. There's a ton of different ways. People have been trying to come up with good equations for friction for a long time, but when you see that C value, we're gonna use Hayes and Williams. And a lot of times in the civil industry, the Hayes and Williams equation is a good approximation for typical water applications, 40 to 75, 80 degrees Fahrenheit. Hayes and Williams is used in the civil industry quite extensively for that. Darcy-Weisbach gets used as well, but that's typically for non-water fluids. It typically gets used for different temperatures. It's a little bit more robust, but Hayes and Williams is a good approximation that gets used a lot in the civil industry and the water industry. So I chose that one. I mean, we could do another problem with Darcy-Weisbach, but I didn't for this session. Maybe another session in the future I will. But so this is where we're starting, and basically what we want to do is we want to find, to supply 100 GPM at 50 psi up at this point, what pressure do we need at this pump? So what pressure are we outletting at this pump in order to get to 50 psi up here? So we have some elevation head we have to deal with. We're going to have some friction losses here, like 2.5-inch diameter hose. That's typically one hose that could be used in like firefighting applications, for example, or agricultural applications, for sure. So we're going to use, if this is our problem, what we're going to do is we're going to use the energy equation here to solve it. So the energy equation, I'll write it here. Energy equation is in the manual, but interestingly enough, when we come back to the energy equation, I'm just going to do a search here. Energy equation, if I spelled it right, and is it going to find me any matches? Maybe. Let's look. It's I thought it was in there. Maybe it's not. Maybe it's just being slow. There it goes. Well, actually, it's not there. It's not fine. Oh, there it is. Energy equation. It's interesting to note that this goes back into essentially the fluid mechanics section. So this goes into the fluid mechanics section. You can see up here it's fluid mechanics. So it jumps back from from water resources, and this is where again, if you're looking at that reference handbook, you got to understand some sections are civil engineering, some sections are going to be fluid mechanics, and you kind of have to know where some of these pieces are. So we're going to take the energy equation and we're going to use it. So let me come back here. What's the energy equation say? The energy equation says essentially that we're going to have P1 over gamma plus Z1 plus V1 squared over 2G plus the pump pressure. Okay, so that's the pump pressure. So we're adding energy into this. We're gonna say that is going to equal to P2 over gamma plus Z2 plus V2 squared over 2G plus the friction losses. Okay. So this is where we kind of have to understand the problem and understand what we're getting into to solve it. But once we know that we're going to use the energy equation, now we can keep going to solve for what this pressure is at the pump. But we also, in order to do this, have to figure out what the friction losses are in the pipe. So let's take a look at each of those in turn. The other thing that we're going to do here is we're going to take a look at elevations. Well, actually, let's jump in. What we know is we essentially have. Let's see what we can cross out first. So we're gonna. I think I forgot a 1 here. So P1. So if we have 0.1, kind of like down at this level, right? So if this is 0.1 and this is 0.2, okay, we're gonna go from 0.1 to 0.2, and basically at P1. We have essentially zero pressure, right? So we have zero pressure. We're at atmospheric pressure. I'm going to cross out P1. I'm going to call this one 0. Okay. P2, we know we want to be at 50 psi. Okay, so we want to be at 50 psi. So we're going to have our 50 psi at P2. Z1, what do we know? We know Z1 is going to be 210. Z2 is going to be 235. And then what do we do for velocities? Well, what we're seeing here is we have essentially a continuity equation that says, you know, we have a Q is AV, a QAV. All of this is 2.5 inch diameter hose, so the A doesn't change, the V doesn't change, the Q doesn't change. Essentially, by continuity, we're going to say V1 equals V2 and just cross those out because we're not worried about the velocity head at this point for this system. Okay, so what we're left with is we really need to, we're trying to solve for this pump pressure. But in order to do that, we're going to have to solve first for the friction losses. So what are the friction losses going to be? Well, the friction losses, let's just take a look down here and we'll say the friction losses. Friction, you know, by, let's go to the Hazen-Williams equation. Right, so friction by Hazen-Williams. And why do I know it's Hazen-Williams? Because I'm given this C value. And you might need to go look up that C value, but let's come back to the reference handbook and come back to our civil engineering section, which I think is maybe around like 292 or so, somewhere in there. And if we keep coming down, we will see our friction head loss. So we have circular pipe head loss expressed in feet, and a circular pipe head loss expressed as pressure, but here's the Hazen-Williams equation. Okay, so this is a general Hazen-Williams equation. We got some different things going on, but the nice thing is you don't have to use the general equation because the handbook gives you this equation down here. Did I go one page too many? I think I did. So let's take a look at this and see what we have. So we're looking at circular pipe head loss expressed, well, we can either do feet or pressure, but what I'm going to do here is we're taking our elevations in feet, so I'm going to convert everything to feet first. You could convert everything to pressures first, but I'm going to start with feet. So I'm going to take this equation and use it. So actually, why don't we snip it? Why not? What's the worst that happens here? So let's snip this in and take a look at it as well. So I'm going to take this this equation, bring it over so we can use it for our head loss. Okay, so what do we get? We're gonna find this head here, and we're gonna say that the friction right is gonna equal 4.73 times L. We're told, I think, in the problem statement that we have a distance of this 200 feet hose of 200 feet. Okay, so that's good. So times L times 200 feet. Okay, divided by C. Our C was 135 to the 1.852. Again, a weird exponent, but it's you just have to know how to type 1.852 into your calculator. Times the diameter. So the pipe diameter. Be careful here because the pipe diameter is in feet. So we're going to do 2.5 inches per 12 inches per foot. And raise that to the 4.87 power. Okay, then we have to multiply all of that times Q, which is going to be 100 gallons per minute, times, to the 1.852 power. But I left a little bit of room here because we have to be careful because our flow's in CFS. So if we're given gallons per minute, we have to multiply. Oh boy. Well, we know that we have 60 wrong way. So we have 1 minute per 60 seconds. And we know we have a certain number of cubic feet or a certain number of gallons per cubic foot, right? So if we have 1 gallon, or how many gallons per cubic foot. Okay, so if you don't know this off the top of your head, you might not know it off the top of your head, right? How many gallons are in a cubic foot? Because this is where we need to do a unit conversion and then raise all that to the 1.852 power. So back to the reference handbook we go. Okay, so this is where knowing, gallon, is gallons in there? I think it is, right? Million gallons per day, that gets us into freight and transport. But here, 1 gallon weighs 8.34 pounds, so we're in the right spot maybe. And what we see is 42, but down here, look, we got cubic foot, 7.481 gallons. Okay, 1 cubic foot is 7.481 gallons. So the good news is we can find that. A search and find didn't take us very long to find it, but what we see is we can cross out our gallons. We can cross, actually, no, we want to keep our seconds. We cross out our minutes, and we're left with cubic feet per second. Plug all this in, and hopefully we get the right answer with all those funny exponents. The number that I got in here was about 13.8 feet. So 13.8 feet. So hopefully that was done right, but let's select those. So 4.73 times 200 divided by 135 to the 1.852, and hopefully you're trying this as well, because the using your calculator can be weird on this, especially when you have your dividing in parentheses and all that sort of thing. But hopefully you can get this right as well. Okay, and then let's see, divided by 60 divided by 7.481, and raise that all to the power of 1.852. Did we do it? Yeah, I think 13.8, 13.82 maybe, 13.82 feet. Okay, so that's the friction loss just in the from the water flowing. Okay, so the good news is we have everything now kind of to plug into our energy equation, so we can do that and we can solve. So let's bring this back down, solve it all out, and hopefully this makes a little bit of sense. So we have 210 feet plus HP, that's what we're trying to solve for, the head of the pump, equals the pressure at 2, right? So we have 50 pounds per square inch, that's what we know we have, pounds per square inch, divided by gamma, which is the unit weight of water, or 62.4 pounds per cubic foot. But do you see a problem here? Units are huge. All right, Jeff, you back? I think I just got something that said my stream got reconnected, so I apologize for that. I'm not sure what happened. That hasn't happened in past sessions, so hopefully it doesn't happen again. And I apologize for that. Thanks for your patience with that. Hopefully this keeps going, and if we have more issues, I will redo the session and repost it. So I don't know what to say with that. But if you're still there, maybe you can just keep putting something in the chat. So I apologize for any weird latency that's going on. Okay, I think we're good again. And so I'm going to keep going here. And hopefully we didn't lose too much. So I apologize for any weirdness that went on with the stream getting disconnected there, but we will keep going and hopefully not have any more issues. So if we do, I will do a repost of this and hopefully make it work. But sorry for any technical issues there. Not exactly sure what happened. So we'll keep going. Okay, thanks for your patience, and let's keep going. So not sure exactly where we left off, but the biggest thing that we're doing is we're just plugging and chugging into the energy equation, right? So as we plug and chug, we have the elevation at the first point. We have a pump pressure at the second point, or the pump pressure that we have to provide, right? We have the outlet pressure that we want. So this is at the outlet now. Right, and then this is our outlet head, the elevation, and then we have our total friction here, which is the sum of the friction loss in the pipe, right? So the friction loss in the pipe plus the friction loss in the fittings. And if not sure where we got cut out, but the friction loss in the fittings is given in the problem statement as 5 feet. So that's going to be something that we have to also add in there, right? Because sometimes those nozzles, the contractions, and maybe whatever there's going to be some 90-degree fittings. You're going to lose some pressure that way. So when we plug all this in, we get a total head of 159 feet. But the problem actually asks for PSI, the pump pressure in PSI, and that's where we need to know how to convert back to PSI. And we kind of did that once already, right? So to convert from PSI to head, we had to multiply by 144 and divide by 62.4. So to go the other way, we're just going to reverse that process. So what we're going to do here is we're going to multiply, times 62.4 pounds per cubic foot, divide by 144 inches squared per foot squared. And what we'll end up with here is this is going to give us a pressure in pounds per square inch. And I believe when we do that out, what we get is 159 times 62.4 divided by 144, and that's like about 69 psi, 68.9 psi, which is going to be most nearly 70. So sorry, don't know what happened with the stream getting dropped there for a second, but it looks like we're back live, and we'll keep going with that. So thanks for your patience. But hopefully this makes sense. We're using the energy equation. We're finding friction, in this case by Hazen-Williams. Could you use Darcy-Weisbach? Yeah, you could use Darcy-Weisbach. If you did, you would most likely be given some friction factor, unless you had to use like the Moody diagram or something like that to go look it up. So either you're going to use this friction value, friction factor. The Moody diagram is given, right? So you can, the Moody diagram is given if you have to go there. So that's another possibility. But hopefully, if you do, you can plug and chug there as well. Okay. So, as we come back to this, though, again, knowing that energy equation, knowing how to put those losses in is going to be key to solving this type of a problem. All right, well, let's keep going, and hopefully the rest is smoother. And what we do here is a flow test is performed. We're on water distribution systems. Flow test is performed with fire hydrant determine the flow rating at a pressure of 20 psi. So static pressure at the hydrant 70 psi. Test uses a hydrant 2.5-inch orifice with square outlet projecting into the barrel of a hydrant. A pitot pressure of 45 psi is observed during the test. The maximum flow rate this system can provide at 20 psi is most nearly. So when I was in consulting, one of the things, like full-time consulting, one of the things that we had to do is we're putting a site together, and we have to work with the fire protection engineers to make sure there's enough fire flow at the site for the building. So one of the things that I was doing is, as I was looking through this, the reference handbook, right, and we come into this, right, and I come back into like, the water resources section. What we get into here is all of a sudden we get to some fire hydrant calculations. And one of the big things for civil engineers is you might not be doing the fire protection system that might fall on your mechanicals, but one of the things as a civil engineer is you're dealing with the water distribution outside, so you have to make sure that you have enough flow for the fire protection engineers. So when I saw this, I was like, you know what, that's one of the things that we had to do in the real world. We had to go to get fire flow tests at our project sites to make sure there'd be enough flow at the site. So we're going to use these two equations here to solve this question. So I'm going to come back and take a look at it, right? But basically the flow test is what we need to do. So the first thing that we're going to do is we're going to find the flow at the hydrant. So we're going to find the flow at the hydrant at the test pressure. So this is kind of step one here. And with step one, this is kind of a two-step process. You might get just only one of these, but at least you're there. And the equation for that one was just Q equals 29.8 times, this is an empirical formula, it's calibrated, but times, if you're looking at your reference handbook, it says D squared and times CD times P to the 1/2. Okay. So the nice thing is this 29.8, it has some conversions in it already, but 29.8 D is going to be our outlet diameter. So we have a 2.5-inch orifice. and D is in inches, times CD, which is a factor for the hydrant coefficient. So if we come back over here, we have a square outlet projecting into the barrel. So that's going to be our 0.7. Okay, so 0.7 times our P, which is our pressure detected by the pitot gauge. So a pitot pressure of 45 psi is what we're going to use. So 45 psi. So our flow at the test pressure, so this is our Q, maybe test, right? This is our Q at our test, is going to be some value here, right? So if we plug that value in, we get 29.8 times 2.5, and I gotta keep remembering those squares. 2.5 squared times 0.7 times 45, and I get like something wrong because I didn't take the 45. I didn't take the square root of the 45. So let me do that one more time, and I get about 875 gallons per minute. So that's the flow during the test. So what do they do at the test? They open up the hydrant, let it rip, and they take a pressure reading and figure out how much pressure is coming out. You convert that pressure to a flow. So that's step one. Step two is you calculate the rated capacity at 20 psi. Okay, so this is about as low as the pressure you want to go and still have pressure to fight your fire. So what do we do here? This is just another equation. So QR equals QF times HR over HF to the 0.54. You gotta love these empirical equations with all sorts of crazy exponents. But what does this look like here? Essentially what this looks like is that we have the test flow, the rated capacity at 20 psi is what we're looking for. We have this HR, which is PS minus P20 and PS minus PR. So, we have static pressure and our residual pressure. And once we have all those pieces, we can come back in here and plug in. But essentially this equation looks like we're going to have our 875 gallons per minute times our HR, which was HR was PS, our static pressure, minus 20 psi. That's the lowest we want to go. And then HF, I'm sorry, is our static pressure minus our residual pressure at our test, so PR. Okay, so we can plug those in, but we get 70, which is our static pressure, minus 20 psi, divided by our static pressure, 70 psi, minus 45 psi. And we raise that to the 0.54 power, and we get a value of QR equals about 1272 gallons per minute. Okay, so this would be the maximum amount of fire flow available at that site, and for where we are at 20 psi. Okay, so 1272 is close enough to 1270 that we're going to go with it. All right, well, no hiccups there. Hopefully our stream is back and not screwing up here, so let's keep going and see where we go. Okay, the next couple questions are concept questions. So, purpose of an emergency spillway. What's an emergency spillway? It sounds like it's used in an emergency. So don't take the bait and don't say that it's for first responders. Okay, so emergency responders, no, that's not what it's for. Emergency spillway is not for that. What is an emergency spillway? Well, at a dam, typically you have some, at a dam, typically you have some normal spillways. Sometimes you'll have some gate structures, right? So where you have maybe a couple gates, and then, so you're going to come down here and this is your dam. And then as you go up from there, maybe you keep going up, and you have like an earthen section of this dam, and then at some point you keep going up. Well, at some point, right, the water level starts to rise. So what we don't want to have happen is we don't want water to overtop our earthen dam, right? So this might be our right. So we might have like a spillway, right? We might have a gated dam, a gated section, right? So the gates can get opened up, so we can pass a whole bunch of flow. We can pass a whole bunch of flow through those gates. We're gonna have some flow coming over the spillway. But what we don't want to have happen is we don't want water to flow over like if this is our, this is our dam here, our earthen dam, we don't want water to flow over our earthen dam. Why not? Because water erodes earth. Okay, we don't want water to flow over an earthen dam. So what we're going to do is we're going to knock out a section of that dam, and we're going to put in a spillway so that as the water level rises, right, we're gonna pass enough flow here so that we never end up going over our earthen dam. So this is going to be like our emergency spillway. Okay, and that's going to be used to control the flood levels. And whether it's an emergency spillway in a dam or it's a water control structure that has a weir to pass flow, which will be in a couple of problems, we'll do that. What this is doing, we're allowing this to pass flow that exceeds the capacity of the principal spillway and protect the dam in the event of a flood. So that's what the emergency spillway is doing. It's allowing us to pass enough flow that we're not going to overtop the earthen dam. Okay, we're not here diverting flows from a reservoir. We're not lowering the levels of a reservoir in the anticipation of a rainfall event, right? This is, you would use gates, potentially to lower the reservoir level. Divert flows, you would again use gates to go into like some secondary channels or something like that. But this is flood control, kind of 101. So hopefully that question makes sense. And this kind of is a spin-off of that question, right? We have a weir that must be sized at a pond. At a pond, I thought I added that, but I must not have. A weir must be sized at a pond to pass flow into an emergency spillway for flood control. Given a weir width of 10 feet, which is smaller than the width of the channel, the approximate depth of flow required to pass 125 CFS is most nearly. So this is going to get us into a weir equation, right? So this is going to get us into a weir equation, and let's come back to take a look at what that looks like here. And here we have some weir formulas. We have rectangular, we have free discharge suppressed, we have free discharge contracted, and we have V-notch. So which one do you use? Well, the good news is they're not crazy different for even the suppressed and contracted, but let me just show you what those look like real quick. But basically what we have is, again, we have this emergency spillway where if you think of, you have a dam, you're going to have some channel that's blocked out here to pass a certain amount of flow, right? So in our case, we have 90 CFS, right? So our flow, our Q is 90 CFS. And we have a width of, we know our channel width, we've got 10 feet for it. And, behind this, we're going to have this water level that's being held back by the dam. Okay, so that's what we're trying to do. And we're trying to figure out how to pass 90 CFS, what this depth of flow is going to be. Right, so that's the depth, or in this case, I'll call it H. Right, so the types of weirs that we have a suppressed, which means essentially the whole thing, or the water flows over the whole channel width. Okay, so this is one version of that. We have a contracted. Okay, an equation for contracted. Contracted looks like this, where we have a weir that's less than the full width of the pond. So in this case, we're gonna have contracted because this reservoir, right? This reservoir is bigger than just the spillway. Okay, so we're going to use the contracted formula. The last one here I'll just show for completeness is you could have like a V-notch, right? So we could have like a V-notch weir, and those are useful because as the flow gets higher, you can pass more flow and less flow as the flow is lower. So this is like a V-notch, and the equations for each of those are in the manual. But the equation that we're going to use here is we're going to go with a contracted. Because our pond is typically going to be bigger than the little spillway that we're going to pass this flow on. Okay, so if we look at that equation, we're going to have Q equals C times L minus 0.2 H times H to the 3/2. At which point you say, I don't want to solve for H. Because that's just a mess. Honestly, it's a mess. There are some approximations, right? There are some approximations. This is not in the handbook. There are some approximations that show up like in the New York State Stormwater Management Design Manual that just says, well, C for a contracted weir maybe is like, 3.1 times LH to the 3/2. So that's a good approximation, but if you don't know it, where do you go? Where I go is this is where I try to cut my losses. I got 4 answers and I've got a calculator. Okay, so I'm just going to plug in because when we come back to the handbook, right? What do we have? We have C for a rectangular weir. This is sharp-crested rectangular weir. It's going to be 3.33. Okay, so what we can do is we can just, we can plug and chug here. I mean, honestly, I think that's going to be the easiest, but plug and chug. Okay, what I'm going to do is I'm just going to stick it in my calculator once. So I'm going to say 3.33 times, what do I have? I have, so this is going to be Q equals 3.33 times 10 feet minus 0.2 times H to the 3 halves. So what I'm doing is I'm just going to plug this in. So I'm going to plug this in. I'm going to say, okay, I'm going to say, well, what Q do I get for each of these heights if I plug them in? Okay, so that's going to be the easiest way I think to do this, because you have a limited amount of time, and solving for H is just a bear. But if I just start plugging in, I do 1.5 feet times 1.5 to the 1.5, I'm going to get like about 59 CFS. Okay, and then the beautiful thing with the calculator is you can go back. I mean, you can put the function in your calculator and look at a table, or you can put each one in individually, and you just hope it's not the last one, because then you just waste it all the time. But even still, it's not wasting that much time. I get 90 CFS. I'm getting closer, and as I go to 2.5, I think we're going to be spot on. So what do I get with that? I get about 125 CFS. Okay, and I could go to the next one too. At this point, though, I would stop and I would highlight it in. I'd say that's good. That's going to give me my 125 CFS. So this is kind of a brute force approach, but sometimes that's what we're looking for, is trying to find how we're going to get 125 CFS with this. Okay, so even with this approximate formula, so we can go back and check this, but with this approximate formula, 3.1 times 10 feet times what, 2.5 feet to the 3 halves, this is going to give us an approximate flow. Again, this isn't in the manual, but it's a reasonable approximation. Times 10 times what, 2.5 to the 1.5. This is going to give us about 123 CFS. So again, it's really close. But this this version of the equation isn't in the handbook. Okay, so this version isn't in the handbook. But it's what I would do here is I would kind of plug and chug this, brute force it, and keep going. All right, so weir equation, I could definitely see that in. I could definitely see it in flood control, whether it's an emergency spillway or it's a water control structure, where you have to limit or you have to provide a certain out discharge at a certain flood stage or elevation of a pond or something like that. It's one of those basics that I think is probably going to be tested. All right, here we go. I threw this one in honor of when I took the PE. When I took the PE exam, actually I had a question that talked about eutrophic water bodies. And I was like, oh man, but I threw this one in honor of that. And also because it does show up in the FE handbook. But when you come into the FE reference handbook and you come back to evapotranspiration, you come back to lake classification, you get some terms in here like oligotrophic and mesotrophic and eutrophic. Right, what do we see with eutrophic? There's a lot of chlorophyll, okay? So we go from 0.3 in a oligotrophic to 3 to 78 in eutrophic, okay? The total phosphorus, we go from 8 to 15 to 386. So eutrophic, a lot of phosphorus, a lot of chlorophyll, because phosphorus is a fertilizer. It makes things grow really well, and especially nowadays when we have a lot of fertilizer out there, and it gets washed into our streams and lakes, it can cause blooms of vegetation and even algae blooms. So when we come back to this question, we say characteristics that lead to eutrophication of water body include all the following except nitrogen and phosphorus rich runoff. Yes, 100%, that will cause eutrophication. Sediment deposition. So basically eutrophication happens when the mineral content increases, right? But if you start depositing soil and filling up a lake, it's going to now have the same mineral concentration in a shallower volume, so you're going to get more minerals, per volume. So that'll cause it too. I'm going to skip high levels of dissolved oxygen because that's the answer. I'll highlight that answer. Actually, high levels of dissolved oxygen is good. When you think about a lot of like ponds around a building, you'll often see a fountain in it. And the fountain is decorative; it looks nice, but it also adds a lot of oxygen into the pond, which helps with decomposition and that sort of thing. But again, an overabundance of plants and nutrients, these two go hand in hand. So more fertilizer into the water, more blooms, a more decomposing mass, which eats up that dissolved oxygen, which is bad for fish and other aquatic life. Okay, eutrophication, one of those concept questions, but I think I personally actually saw that on the PE exam. So something, a concept question about eutrophic water bodies. Here's another one. Stormwater management, right? Standard stormwater management practices, SMPs, for water quality controls are consider all the following except, right? What does it not consider here? Okay, capture and treat 100% of water quality volume. That's water quality. Okay, that's good. Achieve 80% reduction in total TSS. What's total suspended solids? All right, so that works as well. And then reduction in total phosphorus. Yeah, reduction in total phosphorus is good because that's what we're looking for too. So, and then here's another question. Maintain 100-year design storm peak site discharge pre-construction levels. 100-year design storm is not water quality. Once you get to 100-year design storm, everything's turbid. Turbidity, that's another one. A lot of sediment in the water and it's cloudy, right? So that's another one where this becomes water quantity, right? This is a quantity control. This is flood control. This is not water quality volume. That's water quantity volume. Okay, so this is quantity, and that's going to be our answer for this question. Pre-treatment mechanism. That's one of the requirements for in the stormwater management design manual for water quality as well. So hopefully that helps. Garrett, just saw your question. Yes, this is the time and day I'm typically streaming these sessions. So glad to have you along. Hopefully we can keep going without any more hiccups. So let's keep going. We've got a few more questions here. Hopefully we can get through all of them. But provide a minimum velocity when half full, 2 feet per second. A 12-inch diameter sewer pipe with an N value of 0.013. Drop per 100 feet must be most nearly. So this goes back to Manning's equation. So we've used Manning's already. Honestly, this equation isn't much different. So, but here we have velocity instead of flow. So let's write down our Manning's equation and then see what we need to solve for and make sure that we can do it. Okay. So what we're going to do here is we're going to come back and we're going to say the velocity in this pipe based on Manning's. Sorry, let me try to write this better here. Manning's equation for velocity is going to be what? We're going to have V equals K over N times the hydraulic radius to the 2/3 times the slope to the half. So what we're trying to solve for here is the drop per 100. So we're trying to solve for this slope. Okay, in here we can plug and chug. 2 feet per second equals this K value now that we're going to use is going to be 1.486, and that has a bunch of units in it, but that's what we're going to use for U.S. customary units. Divided by our N value 0.013 times the hydraulic radius. So what's our hydraulic radius? Well, we have a pipe that's going to be half full of water. Okay, this pipe is half full. And again, when we're looking at this, we're going to look at the perimeter, the area, and we'll solve this. So if we look at the hydraulic radius of this thing, what are we going to get? Well, we're going to have 1/2 of pi d squared over 4, right? That's the area, but it's 1/2 of it because we only have half the pipe. And then what's the perimeter? Well, the perimeter is going to be 1/2 of what? Pi d, because pi d is the circumference. So we get a bunch of things that cross out. The 1/2 crosses out, the pi's cross out, one of the d's cross out, and we just end up with essentially d over 4. So in our case, the hydraulic radius equals what? We have a 12-inch diameter pipe, and I'm going to say, 12 inches divided by 4 equals 3 inches, which is going to equal 1/4 of a foot. Okay, so then I'm going to come back in here to my hydraulic radius, 1/4 of a foot to the 2/3, and we get s to the 1/2. So once you have all that, you have to rearrange a few different things, but you're going to get s equals what? 2 feet per second. Divided by all the rest of this, 1.486, divided by the 0.013 times 0.25 to the 2/3. And to get rid of the square root, we have to square all of it. Okay. So when we solve that, I think the answer that I got was 0.002. And the units on the slope are feet per feet. And you look at this and you say, oh shoot, none of these match. And that's when you look at me and say, Mattson, did you screw something up? Oh man, and I'd love to say that I did, but I actually didn't here. I actually took this problem from the 10 state standards. So up in the northeast, kind of Midwest, northeast, the 10 state standards are what are used for sewer design, and the minimum slopes are spelled out in the 10 state standards as using the Manning's equation. They actually use full flow, but it's not really any different here. But what this is looking at is Manning's equation for 2 feet per second with an n value of 0.013 per 100 feet of pipe. So this is a foot per foot. What we want is per 100 feet. So we're going to multiply this times 100 feet to get our answer, which is going to be 0.2 feet per feet. And that's going to be our answer. So for every 100 feet, you're going to drop 0.2, right? So 0.2 divided by 100 is going to give us our slope of 0.002. Okay. And so I should say 0.2 feet per 100 feet. I should say it that way. Okay. So that's question 12. Let's keep going. We got a few more here, and let's see how we do. So soil testing indicates presence of an unconfined aquifer with a depth of 180 feet above an impermeable layer. So we've got some stratum here, and this is, we have some groundwater table in this thing going on. So this is some groundwater table, and what we're going to do is we're going to drill 3 wells into here. I chose for groundwater, I chose a well drawdown problem. You could get into some other problems here, but basically what we're doing is out of this one well, we're going to pump out a Q equal to what I said 50 gallons per minute. Okay, so we're pumping out 50 gallons per minute, and we achieve a steady state. So what we're going to do is we're going to start to draw down this aquifer. Okay, and we're going to draw down this aquifer. Okay, so we know that this aquifer is 180 feet tall, and at this point we're 15 feet down, so this is the 15 feet here, and at this point we're 11 feet down, and our distances are 400 feet and 800 feet from the well. Okay, so our water is going to be in here, and it's getting drawn down, right? So it's getting drawn down in each of these wells. We'll see that, coming down, and this is kind of going to be our well drawdown problem, right? And that's what this is kind of look like there. So the question is, how do we solve this problem? This actually is one of those questions that hopefully if you get something like this, you can read the question quickly enough, know where the equation is quickly enough to go to find it. But our well drawdown equation is going to be right here. So it doesn't look exactly the same as this, but it's going to be very, very similar here. So we have an equation here that we're going to be able to use to solve this question. Okay, so let's copy this equation over, and let's go ahead and solve it. So the equation says Q equals pi times K. So that's the K, that's the hydraulic conductivity that we're trying to solve for. Pi times K times H let me write my h a little bit better here, but h2 squared minus h1 squared, okay, divided by the natural log of R2 over R1. So we have most of this, right? What we have is I'm just going to plug and chug over here. So 50 gallons per minute. And we have to do our unit conversion here again. So we have to do 1 cubic foot per 7.48, 1 gallons times every minute there's 60 seconds. This is going to equal pi times k times our height. And this is where you got to be careful with the height. It's so easy just to plug in the wrong number and get the wrong answer. But our height here, we have to look at this. Like the height goes from the point to the bottom of the aquifer. Okay, so from the point to the down, we have the drawdown, which is from the point to the original surface, the groundwater level. So we need to find our height here. And we're going to have, this is going to be like height 1, and this is going to be height 2, but height 1 is going to equal this 180 feet total, minus our drawdown 15 feet, which is going to be 165 feet. And height 2 is going to be our 180 feet, minus 11 feet, which is going to be 169 feet. Okay, so once we have our heights, again, this just becomes kind of a plug and chug thing where it's 169 squared minus 165 squared divided by the natural log of the radius 1. So our radius 2, which is 800 divided by radius 1, which is 400. Okay, so you solve all that, and hopefully you get a value that makes sense. So when you solve all that, we get a value that looks nothing like our values up above, right? We get a value that says k equals 0.00001. Did I miss a 0? I think I missed a 0. 0.0001824. And you wonder, what did I screw up? Hopefully I didn't miss a square this time in the calculator. But actually what you see here is when we look at this Q value, this is a flow rate in cubic feet per second. Okay, cubic feet per second, so feet cubed per second. And what does the question ask for? The question asks for feet per day. So that's what we're tasked with here, is to come up with actually, hold on, let me just double check here. Oh, right, I'm sorry. No, the K value, the Q value is cubic feet per second. The K value is feet per second. Sorry about that. The K value is feet per second, and we want feet per day. So this is feet per second. I was thinking some of the units were wrong, but this is feet per second. We want feet per day. So how do we get days? Well, there's, 60 seconds in a minute times 60 minutes in an hour times 24 hours in a day. And K is going to equal, I think it works out to be roughly 1.6 feet per day, which is a typical kind of value out there too. So hopefully this works for you. All right, we got just a couple more questions here. This one's a water quality type of question. I could have thrown in a Darcy's Law question equation here because sometimes sand filters are used to filter, water quality. Honestly, I knew this was going to be long anyway, and I didn't get that one in there. Maybe for a future one, I'll get Darcy's Law in. But primary purpose of the National Discharge Pollutant Elimination System in the United States. So anywhere you go, you're going to be run into NPDs, and this is going to be something that you're going to have to deal with on sites to maintain water quality volume. This is a result of the Clean Water Act. Like back in the 70s. The Ohio River lit on fire, and people didn't like that. They said water shouldn't be lighting on fire, and as a result, that was sort of one of the catalysts that led to the Clean Water Act. And each of these answers here is a result of the Clean Water Act. But specifically, NPDs is the pollutant discharge elimination system is controlling point source discharges. So that's what this permit does in every state. Some states have their own system. The federal government will regulate that to states. Like in New York State, there's a SPEEDI system, a state pollutant discharge elimination system. But then the other pieces of these, right, the other components of these were all, right, so these are all results of the Clean Water Act. So Clean Water Act was put in place to protect water quality. You see that even now, even with some of the lead in the drinking water, and you see, Clean Water Act stuff going on. That's looking to mitigate some of those problems. But new technologies, standards for contaminant levels, communities, helping communities construct treatment plants, and even now you see federal government reaching in to help communities replace water lines, especially lead-tainted ones. So Clean Water Act covers a lot of things for water quality, but specifically here, we're looking to control pollutants from point source discharges for the NPD system. Okay, so let's keep going, and this gets into basic chemistry. So honestly, I'm surprised a little bit that the Civil FE doesn't have a chemistry section. Every civil program needs a chemistry class. You take a chemistry class, and this is kind of where I think it'll show up is when you get to kind of water quality. So what we have here is some kind of basic stoichiometry, and honestly, stoichiometry is not at the top of my list for things that I'm super an expert on. So if I screw something up, put something in the comments, let me know. But what we have here is lime soda softening is used to remove calcium carbonate hardness for a given water source. So there's a lot of calcium in this water, and you add a whole bunch of lime to it to precipitate calcium carbonate, right? So the dosage of lime required to combine 50 milligrams of calcium is most nearly. So this goes into stoichiometry, and if you remember stoichiometry, what we have to do is we have to look at the reaction and figure out what to do. So you might be like me and wondering, like, what's calcium carbonate? So calcium carbonate, if I look at that, I find something and I search it, and magically something pops up. So I think when you get into some of this like basic chemistry stuff, some of the equations are already in the reference handbook, right? So we already have this equation, and that's going to be a good thing, because honestly, I probably wouldn't remember this otherwise. Okay, but this is the equation that we're going to use, and then we have to basically use some stoichiometry to get go from one thing to the other. Okay, so if I bring this over here, basically what we have is we have 50 milligrams per liter of calcium. So let's just start there. Okay, so what we have is 50 milligrams per liter of calcium. So calcium's just, the calcium ion. And what we're going to do here is calcium. And what we want to do is we want to use stoichiometry to go from this, right, to essentially we want to get to how much lime we need to add to this. So lime, this is what we're going to do, is we're looking for lime. How much, oops, that didn't work. Let me come back here for a second. How much lime do we want to add to this thing? And this is our lime. So we want to go from calcium all the way over to lime. How do we do that? Well, anytime we get into stoichiometry, we first have to take this and multiply it by, essentially, we want 1 mole of this is equal to what's our molecular weight of our calcium, right? So our calcium has a molecular weight here. And if we come back into our reference handbook, what we see here is we have some basics, right? So we have some basics like calcium 2+, right, is 40.1, molecular weight of 40.1 per mole. Okay, so I can come back now and I can say, well, that's going to be 40.1 grams. And don't worry that milligrams and grams don't cancel out, because we'll get back there in a minute. But so we know that we have 1 mole is this. So we're starting some conversions, okay? And actually 1 mole of, let me keep the calcium. Let me keep the calcium here as well. So we have 1 mole of calcium is 40.1 grams. So now what are we doing? Well, we're saying for every mole here of calcium that starts, right, we need to add 1 mole of calcium hydroxide. So what we're really doing is we're saying, well, for every 1 mole of calcium, we're going to have 1 mole of, calcium, what's this, hydrocarbonate, calcium CaHCO3 2. Actually, let me put that on the top. Right, so for every 1 mole that we start with, we really have 1 mole of this hydrocarbonate. for every 1 mole of our calcium. And then we're going to multiply this. Well, what we really want, though, is our calcium, our hydrated lime here. So we're going to say for every 1 mole of our calcium hydroxide, we have 1 mole of our lime. And then we need to keep going. So now we have 1 mole of our lime is equal to what? Well, again, we have to come back here and we have to say the 1 mole of the calcium hydroxide is 74.1 molecular weight. So this is 74.1 grams for the calcium. I'm sorry, for the lime. Okay. Big, long stoichiometric equation, but the cool thing is everything starts to cancel out. So the calcium goes away, the calcium goes away, the calcium hydrocarbonate goes away, this lime goes away, and we're left with, all our moles here go away, and we're left with essentially even our grams go away. So we're left with an answer here. When we do all this out, we're going to do, essentially it just works out to be essentially like what, 50 divided by 40.1 times 74.1. Okay, so if that makes some sense, we get 50 times, 74.1 divided by 40.1. We get an answer of like 92.4 milligrams per liter of the lime. But don't pick this answer. And the reason is because you have to read the question. Here we have 80% purity, so the lime is only 80% pure. So the lime's only 80% pure. Let's take the 92.4 milligrams per liter divided by our 80%, and we're gonna get one other value here. That's going to be about 115.5 roughly milligrams per liter of the lime. And that is our final answer for that one. Okay, so again, the stoichiometry, if you don't remember it, go back and there's a couple good videos probably that can explain it better than me on the chemistry side of this, but hopefully some of this stuff is coming back to you, or you remember a little bit from that chemistry class that you took. And if you have some, maybe some ratios here where you don't have a 1-to-1 molar ratio of these things, you can, use your conversions to do them a little bit more easily. But we haven't talked to a few people that have taken the exam recently. Water softening, water hardness, these types of things did show up on the exam. I don't know the specifics of the questions, but those topics were there, so I wanted to get them in there, and specifically in this section. Okay, and then 2 questions left, and we will send this one and be done. So where do we go today? So what we have here is BOD. Again, talking to people that have taken the exam recently, they, not specifics, but BOD was one of those things that showed up. So here we have an unseeded domestic wastewater. BOD test is performed. So what do? You take a 300 milliliter bottle, right, and you add a small sample of, your bad stuff, your wastewater. You fill the rest of this with clean water. So you dilute it, and then you start taking some measurements, right? So you start taking some measurements, and you get some readings here. So what are you reading? You're reading the dissolved oxygen content. Okay, so this is kind of your BOD test. You set it up, you let it sit for 5 days, you measure it again, and you get a second reading. Okay, and what we're asking here is, well, what's the ultimate BOD? What's the kind of the ultimate BOD in this sample? So maybe, again, you don't really remember your environmental class too well, and that's okay, I don't either. I'm just being 100% honest with you. But the thing is, some of these basic concepts, can you just look up BOD? Maybe, but man, there's 156. So BOD 5, does that ring a bell? Oh man, look at that. BOD 5 does start to show a couple things in here, which is good. So that puts us into the environmental section, which is good. Okay, we don't want a mixed lagoon. We're not doing lagoon design here, but it puts us in the right section. So maybe you don't remember what BOD is. BOD is kind of a measure of biochemical oxygen demand, right? And this is where I wrote down where we need to go here. So I think I went by it already. So let me come back here and let me see where we are. There we go. So the BOD test solution and seeding procedures. So here we have a BOD and milligrams per liter. We have dissolved oxygen 1, dissolved oxygen 2 divided by P, which is the fraction of the wastewater sample. Okay, so if environmental is not your first language, that's okay, but you do, if you know some of these basics, it will help you on the exam to get some of those points that maybe you otherwise wouldn't get. So let's first start with this, right? We have the BOD, and specifically we're going to do the BOD 5 here. It is going to equal D1 minus D2 over P. So what's this? It's the dissolved oxygen, at 1 and at the time that we're looking. So what we have here is dissolved oxygen 8 milligrams per liter minus our 4 milligrams per liter divided by P, and P is that fraction, right? So in this one we have 6 milliliters of the wastewater. We have 300 millimeters or milliliter sample or bottle that we're going to be using. So we take 6 divided by 300. We could keep our milliliters in here just for unit consistency, but that gives us our BOD 5 of, I think this works out to 200 milligrams per liter. So you could stop there and say 207, great, but don't do that, because the ultimate BOD isn't just the BOD 5. What we want to do is we want to go to the next equation here, which is going to help us as well. And specifically when we come back to what we're looking at, I'm just going to type in ultimate BOD. Okay, so ultimate BOD, this gives us a BOD exertion. Another formula that is kind of one of those basic formulas, is a basic test for BOD. That's why I'm trying to get, the environmental section's so big that there's a separate environmental FE. This is not intended to be an environmental FE review by any means. Okay, but hopefully it gets some of the basics. But what we're seeing here is that L naught is that ultimate BOD that we're looking for. So I'm going to come back here and I'll say the BOD, in this case, I'm going to say the time T5 equals the ultimate BOD times 1 minus e to the minus kt. Okay, and let me put my parentheses in the right spot here. So what I'm going to do is I'm going to take this value that I just learned, I figured out here, I'm going to plug it in. So I'm going to get 200, I'm going to get 200 milligrams per liter equals our L naught times 1 minus e to the minus k. And what's k? Again, this is where you're going to want to take a look at this, but hopefully you've read the problem to see that the k rate is 0.3 per day. So that's good. We do 0.3 per day times our 5-day test. And the good news is our units work out here, and we end up with coming up with L naught. You divide 100 by this mess, and what you get, I believe, is about 257 milligrams per liter. Okay, so that's the total ultimate BOD that eventually gets solved for. Man, we're fine. Why not? Let's go to one more. But hopefully that makes a little bit of sense. I mean, honestly, if I had to pick some basic wastewater type things, I think BOD is going to show up. I think you're going to see, whether this is fate and transport or it's a BOD test or something along those lines. Wastewater, there's a couple different topics that you could throw out there. It's going to be a couple questions on the test. It's not going to be overwhelming, but it's one of those things where if you can get them, that's great. If not, I wouldn't spend a whole bunch of time studying all of environmental, because like I said, there's a whole test just on environmental. But if you can get some of these basics down, I think that's going to help you. Here's another one of those basics that I think that's useful, but this is the last question here. We have chemical analysis water sample indicates calcium and magnesium. We have different concentrations, 10 milligrams per liter and 25 milligrams per liter. What's the total hardness of water expressed as calcium carbonate? So again, this kind of goes back to that stoichiometry. What we're doing is we're trying to take one thing and convert it into something else, right? So this goes back to that stoichiometry. And what we see here is total hardness in water is essentially the sum of the calcium and the magnesium. Okay, that is our total hardness, which is what we want to solve for. So if you get other things like other chemical analyses that give you other components in there, minerals in there, the calcium and the magnesium you want to pull out for the total hardness. But to convert this, what we're going to do is we're going to take the grams of substance A and multiply it by, or the milligrams in this case, the milligrams per liter of substance A, and multiply it by the equivalent weight, right, of the calcium carbonate divided by the equivalent weight of the element. Okay, so here we have two things. We have the calcium and we have the magnesium, and specifically we have 10 milligrams per liter and 25 milligrams per liter. Don't just add those and say 35. I'm done. I don't want to do that anymore. All we have to do here is we have to multiply by a ratio. So let's go and find our equivalent weights here, and we can come back and where is that? That was calcium carbonate, right? So if we come back to calcium carbonate, we come back to this table, which is nice because this gives us our calcium carbonate, which we could use the 50 or the 100.1, and then we can use for our calcium we can use the 20 or 40.1. We have to pick and choose. It's kind of like mass versus weight grams. I'm probably saying that wrong, but we're 2 hours in, so let's just keep going with it. But you can see the ratios here: 100 to 50 and 40 to 20. They're similar ratios, so it's not going to make a difference. So let's go with this. So we're going to pick, the calcium carbonate is 81.1, and the calcium is 20. So let's is that something? Did I say something wrong? Calcium carbonate's 50. Sorry, calcium carbonate's 50 and 20, and the magnesium is 12.2. Okay, so let's come back and finish this one, send it, and be done. So we have 50, 50 over 20. This is the 50 of the calcium carbonate over 20, the equivalent weight of calcium. And we're going to multiply this one by, I think, 50 of the calcium carbonate divided by 12.1 of the calcium. And we get a couple values here. So the values that I get here is 10 times essentially what 2.5 is going to be 25 milligrams per liter as the calcium carbonate. And we end up with 102.5 milligrams per liter as calcium carbonate. We add those up to get our total hardness, and our total hardness is going to be about 127.5 milligrams per liter total hardness. And we did it. So we got there. There was, I don't know, we'll see how the recording does with everything, but hopefully I can trim that middle section out where the recording and the stream hiccuped. But hopefully this is helpful because there's a lot in here. I mean, everything from Mannings to Hazen Williams to, we didn't get to Darcy Weisbeck, but there's some of this water chemistry in there as well. There's a lot in this section, and hopefully, when you're all said and done, you get 10 to 15 questions in here. I mean, there's A through K is close to 10 to 15 right there. So if you get one question per each, I tried to lay out some of those conceptual questions, some of the more technical questions, some of the ones where you use weird exponents, some of those empirical equations and weird units that you have to work through, because it can be a challenge. It can be a challenge, but I think you guys can nail this section. You can get it down, and you can be number one. Which reminds me that wastewater jokes really aren't my number one choice, but they are a solid number two. Sorry. Okay, I had to do something just to lighten this up a little bit. And you know what? I got one more joke here that I found. and it's not mine. I can't take credit for this, but it's funny. So I'm just gonna say this one just to send us off with a laugh, hopefully. So there were passengers on a small plane that were sitting there, and then the pilots came in. But the pilots had, you know, big dark glasses on. One had a cane, one had a seeing eye dog, and they go up to the pilot or the you know, the cockpit. They close the door and they start taxiing down the runway. And everybody starts getting nervous because what they see is a big lake in front of them at the end of the runway. And so as they're going down, they're still going down, they're still going down, they're still going down. So they start screaming because they just get really mad because they start worrying for their life because they're going into the pond, and they're gonna, you know, they're not gonna do so well. But all of a sudden, plane picks up, starts going up, and everybody breathes a sigh of relief. In the cockpit, the pilot turned to the co-pilot and said, "You know, Bob, one of these days they're gonna scream too late and we're all gonna die." Get it? They couldn't see. Yeah, so anyway, they couldn't see the lake, but at least everybody screamed. So, oh man, not so funny, but funny. Maybe that's a solid number 2 joke. Who knows? But that's it. So hopefully this review helped you. Hopefully the problems are a good refresher on a bunch of things, and you know, we can keep going. So next week we'll be on to transportation. I've got some good problems there. And Jay, man, you remember my test from transportation. So this is going to be my transportation analysis test from actually, I think I'm going to take problems from your test. So why not? This is good. But transportation should be fun. Again, a million equations. About 2 million variables, but it should work. And thanks for hanging on to the end here. And hopefully these reviews are helpful to you guys. So, hey, if you have anything in between, you know, drop me a line, drop a comment, and we'll go from there. So, thanks for everything, and I'll see you next time. So, till next time, keep working hard and moving onward and upward.